Okay, so this is a lecture about nutrient management planning and optimizing phosphorus and potassium fertilizer rates in the UK. And it's one I'm recording because I can't be here on Monday to give the lecture in person. But we'll have a practical class later this week, and we'll cover a lot of this in that class as well. And you'll get some hands-on experience in how you come up with phosphorus and potassium fertilizer rates. So hopefully that'll be okay, and you'll be able to understand how it's done. So key topics in the lecture. First of all, you can have a look at Wheel and Brady, chapter 14, and have a look at the soil phosphorus and potassium cycle. So you have that kind of fundamental knowledge of how phosphorus and potassium cycle through soils and crops. So phosphorus we covered already in a lecture earlier this week, but potassium we haven't done yet. So that's one you might want to read about a bit more. It's quite a bit simpler than phosphorus and nitrogen as well, in that it exists primarily as the cation K+, which is the form that's available to crops. And of course it's involved in cation exchange, as we've covered, and there's a few different sources of inputs, but it's not it doesn't sort of transform and change into many different forms like nitrogen does, for instance. It's usually in that K+ form, just tied up in organic matter or clay minerals. Anyway, we'll talk about that more when we get to that lecture, but I think it's for what we're going to do about nutrient management. You don't need to know the details yet of how it cycles through the soil too much. Also, we've got this RB 209, which is the Bible really of fertilizer recommendations that in England and Wales, and there'll be something similar used in Scotland and Northern Ireland as well, and definitely the principles of fertilizer recommendations will be the same in those places. So we'll talk about some of the theory and principles, plant responses to nutrients, economic optima, break-even ratios, luxury consumption, and Liebig's law, and then some good practical information on how we come up with those fertilizer recommendations and what are good nutrient management practices. So first of all, so the theory here's a typical nutrient response curve. So this is a curve showing how crop yield, which is on the y-axis, responds to increased nutrient supply. And you can see on the x-axis that nutrients come from the soil. Of course, soil always has some natural fertility within it, and then there's additional nutrients in agricultural systems we tend to apply as fertilizer or manures, because we're really aiming to get quite a high level of productivity from that crop. So we need to supply some extra nutrients. So you can see that response curve shows that as the supply of nutrients gets larger, moves to the right on the x-axis, the crop yield on the y-axis increases, right? But it's not linear, it's sort of curvilinear, and it reaches a maximum at some point, which is point C, you can see there, and then it actually starts to decline after that. So you can see that more nutrients don't keep increasing yields indefinitely, right? At some point your crop will max out, and then you may actually start to get diseases and other problems that cause a decline in yield if you have too much of a nutrient there. And you can also see from that curve that we don't actually fertilize to maximum yield. We fertilize to what's known as the economic optimum. So that's point B on the curve, and that's based on the value of the crop and the cost of the fertilizer. And so you can see that as you increase nutrient supply, there's a diminishing return there, right? You can see that for every additional kilogram of nutrient you provide, you're getting a little bit less yield. And at some point, what you pay for that fertilizer is not actually going to be recovered in the value of the crop that you harvest. So at some point, you're not really making any sense to spend more money on fertilizer to go for super high yield. So that's we actually determine that point of sort of optimum fertilizer rate based on what's known as the break-even ratio, and that's the ratio between it's basically the crop yield needed to pay for a kilogram of nutrient, and it is calculated as shown in that formula below there, where you put the cost of the nutrient divided by the value of the crop. So that's the crop yield you need to pay for a kilogram of nutrient, and that. So yes, you can calculate your own break-even ratio if you know the cost of your fertilizer and the value of your crop. So here's an example from RB209 showing ammonium nitrate. That's 250 pounds a ton, which comes out to 72 pence per kilogram of nitrogen, and wheat when it's worth 120 a ton. And if you do that calculation, you'll find you get a break-even ratio of 6, which means that for every additional kilogram of nitrogen that you apply, you'd need to get an additional 6 kilograms of wheat yield to pay for that nitrogen. So if your cost of your, or value of your crop changes quite a lot, or the cost of fertilizer changes quite a lot, you may want to calculate your own rates, adjust the rates somewhat, at least, because the rates in RB209 are, have been calculated, well, when it was produced, which is a couple of years ago now, and so those ratios may have changed a bit. I mean, on the whole, most people don't do that, but it is possible to do that, and there's a little more info in RB209 on how to do that, actually. But the main thing is to understand this idea of the diminishing returns as you put more and more fertilizer on, and how it really depends on, the optimum rate really depends on those two things, what you're paying for your fertilizer and what your crop is worth. And those were some links, which I don't think they're live now, on current fertilizer costs and what wheat is currently valued at. So, but you can have a look at that and see calculate your own break-even ratio, and then think about if the price of N goes up, what are the impacts of that on your fertilizer rates that you'd want to use. Probably want to cut back unless the value of your crop goes up as well. So that's a few things to think about. Getting into economics there a bit, and I think Jeremy Franks has probably covered some of this with you in modules last year and maybe this year as well. Now, the other concept I wanted to talk about is luxury consumption. So that's absorption of a nutrient in excess of amounts required for optimum growth. And we usually talk about it with regards to potassium. So potassium is a nutrient that crops can take up in excess. And it just seems to sort of, it's easily taken up in soil water, and plants will take it up more than they actually need for optimum growth. So this figure is a little complicated, a little maybe difficult to understand at first glance, so I'll just talk you through it a little bit. It's one of these strange graphs where you've got two y-axes. On the right you've got a y-axis, which is the relative plant growth or yield, and on the left you've got a y-axis that's the potassium content of plants. So there's two lines on the graph that are relevant for each of those axes. So the relative plant growth or yield you see has been pointed out. It's actually, I'll just mark it here with a little red dot. Here you can see, whoops, that's a bit of a squiggly line, but anyway, that's relative plant growth. So that green line is the growth, obviously, of the plant, and you can see along the x-axis, as you increase potassium available in the soil, that growth increases up to a point, but then you can see it maximizes right about there. And then beyond that, you're not getting more yield, even if you have more potassium available in the soil. But then the potassium content of the plants, and you can see that this one here is continuing to increase with more potassium available in the soil. So it increases beyond that point where where maximum yield is reached, and that's sort of this point here, I guess. That's the point where you get maximum yield. So beyond that, you can see this luxury consumption of potassium, really, where the plant continued to take it up, but the yield didn't increase any further. And that can cause problems, because it then can impact on uptake of some other nutrients, calcium and magnesium, for instance, and you can end up with this situation where it inhibits uptake of magnesium and calcium, and you end up with this hypomagnesia or grass tetany. It particularly happens in grasses, sort of pure grass stands, where the livestock end up not getting enough magnesium. And they can end up actually sometimes dead, in fact, so not a good thing. Now on to some more theory. So Liebig's law of the minimum, and you may have seen this image of the barrel before. It's really a popular image that's used when we're talking about plant nutrition. It's basically showing that the yield of your crop is only going to be as high as the nutrient that's in the lowest supply, if that makes sense. So the different staves on the barrel are indicative of all the different nutrients, and you can see the water level in the barrel is sort of crop yield. So if you the lowest stave, that's where the maximum level of the water or the maximum yield you can achieve. So in this little image here, you can see phosphorus here is kind of the limiting nutrient in that case. It's not sufficient for a yield higher than that, even though these other nutrients are. So this is sort of how it's defined. A plant's development is limited by the one essential mineral that is in the relatively shortest supply. And that's why we have to look after supply of all essential nutrients. And yeah, Liebig is considered the father of modern fertilizer theory. And you can tell by what he's wearing that was probably quite a few years ago that he came up with this law, sort of back in the late 19th century. So on to how we actually come up with phosphorus and potassium fertilizer recommendations. So a few things about terminology, first of all. I think I alluded to this in the phosphorus lecture. There's sort of an annoying convention of referring to nutrient contents of fertilizers, material, and rates of nutrient application on crops in terms of the oxide of phosphorus or potassium. So P2O5 is the oxide of phosphorus. It's not a form of phosphorus that actually exists in reality, but it's just a standardized unit we use when we're expressing nutrient contents of fertilizer materials. And the same with K2O. This doesn't actually exist in reality, but when we express the value of fertilizer nutrients, we always express them in terms of K2O or P2O5. Soil and plant analyses are generally done in P as the actual element, so P or K. So that's a bit confusing. You have to be aware of that when you're looking at some of the results of lab analyses, especially say on a manure. You have to be careful and check whether they've reported manure P and K contents as P or as P2O5 and K2O. That's just a reminder that you should know how plants take up phosphorus. So we covered that in our phosphorus lecture. Remember, we talked about H2PO4, H2PO4 minus 1 and HPO4 minus 2, the two forms of phosphate. Potassium is taken up as K+, so that's an easy one. And we'll talk about that more in our potassium lecture. So some of the principles of good nutrient management, I'm sure we all know this, things like soil testing regularly. So we did a bit of soil testing in the lab this week. We looked at potassium, which is a fairly easy nutrient to measure in a lab. So we did that extraction, and hopefully you've calculated the potassium concentration in those soils and maybe even converted that K concentration to a K index, which is what we actually use then to come up with a fertilizer representation. And you try and get a representative soil sample. There's an image of sort of a bit of a random path taken across a field, and then mixing you would then mix that into a bucket and submit probably one sample to the lab. That image shows how you typically divide fields into similar management zones. And so, yeah, how many soil samples do you need to take and send to a lab? You want to get a representation of a field, of an area that you're going to manage differently than elsewhere. So if you're going to manage, apply a single rate of fertilizer across a 20-acre field, then you would only need to send really one sample in for analysis, but you would still collect a lot of samples to represent that field, mix them really well in the bucket, and then send the one off. How deep? Usually you think about probably the topsoil, the plow layer is usually the depth that you tend to take a sample from. So keep that in mind too. If you're min-till, you might be going not so deep maybe, although maybe the rooting depth is generally, you're looking at the top 20 to 25 centimeters really, which is where most of the roots of the crop are concentrated, and that's probably the best area to be sampling to. So how do we then use that information? So we do soil testing to get levels of available phosphorus, potassium, and sometimes magnesium as well. We also going to monitor pH like we did in the lab. Soil organic matter can be very useful to monitor as well because it gives you an indication of the general health of the soil. which we talked a little bit when we did soil biology about that, and also you will look a little more at soil carbon in future lectures in this module. Because phosphorus and potassium doesn't change really rapidly from year to year, you don't need to test it every year. You can test every 3 to 5 years, and that's sufficient. And then, soil testing for nitrogen, which we'll talk about a little more in the next lecture, but that might be done more often. So sometimes we do winter soil testing for nitrogen for mineral land, but we'll get into that in the next lecture. Then we want to use a recognized fertilizer recommendation system. So that's RB209, the old hard copy of the manual. As I said, it's now available as a download at the AHDB website. So it's been updated a bit, but we still call it RB209. And of course, it's important to account for nutrients supplied in organic manures or organic wastes. So we'll talk about that a little more in the practical. Keeping accurate records, that's important, of course, as well. Records of soil test results, nutrient applications, crop yields and rotations, etc. And those are just some logos for some of the different software that's out there to help you make nutrient management decisions. Crop Walker, Farm Plan. Planet's sort of a bit obsolete now. That was a software tool we used to actually use in our teaching here, but not really used too much anymore. But they all, anyway, were based on RB209. So they were just kind of handy tools to help you look up values in RB209 for fertilizer rates, depending on the soil test results you had. So when you're doing phosphorus and potassium, you do your soil test, and then you have to figure out phosphorus or potassium index using soil test results. So you take that value from the lab, like we've done in the lab for potassium, and then you look at a table and see what range it falls in, and then determine which index it is. From 0 is the lowest, going up to 4, 5, 6 even. And then you use that index along with a crop recommendation table. And there's a note, actually, again, coming back to that terminology, P2O5, K2O, etc. It said this is because the concentration of phosphorus and potassium are expressed in this way in fertilizers. Makes it easier to calculate the amount of fertilizers applied. Yeah, that's right. So that's why the recommendations for crop production are in the same unit. So you shouldn't need to convert from one to another, and that's a good thing. Here are the indices. You can see there the table below. So you take your soil test result in milligrams per liter and read across and get an index. In arable crops, we're aiming for an index of about 2 for phosphorus and potassium. So that means if you have an index right now for phosphorus or potassium of 0 or 1, then you need to put on some extra fertilizer to get that index up to 2 gradually. Once you have an index of around 2, then you still put some fertilizer on, and that's what we call maintenance applications, which are just enough to replace the nutrients that the crops removed every year. Here's an example of what a table looks like. So here you can see, first of all, it's cereals, and this is for phosphorus and potassium on the same table. And they're winter wheat, winter barley, spring wheat, spring barley, winter or spring oats, so the main cereals grown in this area. And then you can see there's 2 categories. So if you're going to plow in your straw, then it's a slightly different rate of fertilizer you need to put on than if you're removing the straw. And it's actually a little less, right? Because if you're returning straw to the land, then you're returning some nutrients. So you don't need to put quite as much fertilizer on to replace the offtake or remove of nutrients. So you can see there, just in red, has been highlighted. If you had an index of 2 and you were growing, let's say, spring wheat with an index of 2, you'd need to put on 45 kilograms P2O5 per hectare. Or if your potash index was 2. Now with potash, by the way, we do divide up that index into 2-, which is lower, and 2+, which is on the high range. So if you get a soil test result back, you may sometimes get a 2- or a 2+ rather than just the 2 for values for your potash. This shows you index of 2. It's possible that you could have a field with a phosphorus index of 2 and a potassium index of 0 or something like that, right? So they don't always fall in the same column. Where do we get our nutrients from? So phosphorus comes from mined rock phosphate. That's an image of a huge phosphate mine in North Africa. And I think I mentioned this in my lecture about phosphorus. A bit of concern around the world about the instability of some of these areas where the phosphate is mined. Some of them are areas where there's quite a lot of political instability or civil war, and so that really puts the whole global supply of phosphate at risk and makes the market very, very sort of uneasy, and is why sometimes the price can go up quite a bit if there's any sort of civil unrest in these areas where they're mining the phosphate. That little green box is showing just some of the more common sources of phosphate from well, not all from bags actually. Superphosphate, triple superphosphate, bag fertilizer, ground rock phosphate is sort of unprocessed raw materials, and then basic slag is a byproduct of industry that also can be used as a P source. But you can see the different concentrations of P2O5, and that's that's sort of the nutrient in the content of those fertilizers. As I said before, not actually in the form of P2O5, in the form of different phosphates that are reasonably well available. And then there's also, of course, diammonium phosphate, where you get nitrogen and phosphate together. So you can see 18-40-60, that's 18% nitrogen, 46% P2O5, and then 0% K. Yeah, a useful thing to remember when you're doing your calculations later, when you see that percent P2O5, just remind yourself that means every 100 kilogram of fertilizer contains that number of kilograms of P2O5. Potash mostly comes from mined potassium salts. There's an image, I think that's from a potash mine in Canada, actually. Really deep salt mines, basically. Always think they're probably quite pleasant places to work, not like a coal mine with sort of not, risks of explosion or dangerous fumes to inhale. They're just salt, basically, that's being tunneled through and extracted. So that's KCl, muriate of potash, one of the most common potash sources that we use in agriculture, 60% K2O. Sulfate of potash is another one, and then some other less common minerals, kainite and sylvanite. And now, polyhalite I have there as well. And I think that's a live link. You might want to take a look. You may have heard recently in the news about this mine in North Yorkshire, which is a polyhalite mine, which was going to be the biggest potash mine in the world. But just recently, I believe they had some problem with investors, and I think maybe that project's been put on hold for now. But that's another source of potash, potentially, if that mine ever gets into production. Huge reserves. Apparently they'll rival the potash reserves in Canada. Okay, so how do we calculate phosphorus and potassium fertilizer rates from single nutrient sources? So this is a relatively easy calculation. I'm just going to show you here how I tend to do this. And I know not everyone does math the same way that I was taught to do math years ago. I tend to always want to put the units of whatever I'm having in my calculation in the calculation so I can keep track of them. So here, for instance, we've got 90 kilograms P2O5 per hectare is needed, and we're going to use triple superphosphate. So how much triple superphosphate do we need? So I would write it out like that, where I take 90 kilograms multiplied by the triple superphosphate percentage. So 100 kilograms of triple superphosphate has about 47 kilograms P2O5. So I would do it that way. I'd multiply 90 times 100 divided by 47 and come out with 192 kilograms triple superphosphate per hectare. The reason I like to do that is because, I'm not sure if I animated this in. Oh yeah, I did animate it in. Is that then you can cancel out the units. So you can, if you have a unit kilogram P2O5 on in the numerator and you have it also in the denominator, so in the bottom part of the formula, those two cancel each other out, and then you'll see you end up with a unit of kilogram. You basically got kilogram triple superphosphate per hectare, and that's what you've got left over here, and that's what you wanted, right? So then you know that you've done the calculation correctly. So that's why I tend to set them up like that, to make sure my units cancel out. But I know that not everyone intuitively does math that way. I mean, some people can intuitively do it without putting the units in and get the right answers. So if you're confident you can, then go ahead and do it whatever way works for you. Same kind of idea with muriate of potash. You can put up the formula 104 times 100 over 60, because muriate of potash is 60% K2O, and then those cancel out, and you get 173 kg KCl per hectare. I guess a good way, just to double check that you've done things the right way around, right, that you've multiplied rather than divided, or vice versa, is that the number of kilograms of fertilizer per hectare should be more than the nutrient need per hectare, because none of our fertilizers are pure nutrient, right? They're always diluted with some other stuff. So you're going to need more fertilizer than the nutrient need. And of course with potash, or triple superphosphate, which is about half P2O5, it's not surprising that we ended up with about twice as much TSP as needed compared to the nutrient need, because it's only half P2O5, if that makes sense. We'll do some practice of these in the practical class. Now, enhancing phosphorus management. So we talked a little bit about mycorrhizal associations before in the phosphorus lecture. So anything you can do to enhance those is a good idea. We talked about some inoculants. Jury's out on whether they're a good idea, but you could legitimately suggest that's something you could try. Avoiding too many brassicas in your rotation, avoiding tillage too much, which disturbs the mycorrhizal fungi. These things can improve phosphorus efficiency and uptake. You can breed for phosphorus efficient plants. That's kind of a long-term strategy that the industry's really sort of taking on board more and more, and that usually involves really selecting for plants that have good rooting systems, that are quite fibrous and effective at tapping into which just sort of penetrating the soil and creating a good volume of soil that's accessed by the roots. Adjusting phosphorus applications based on soil tests, that's kind of obvious, isn't it? We've talked about that. Makes sense to only put on what you need. You can band fertilizers, so that's placing the phosphorus just where the crop needs it. That's quite important. It makes sense because phosphorus doesn't move in the soil. I think you should remember from the phosphorus lecture how I talked about how it reacts with a lot of minerals, surfaces in the soil. Sometimes we think of it as a sticky nutrient. So we need to put it fairly near to where it's needed, especially for seeds which don't have root systems at all. They need to be able to come in contact with that phosphorus pretty quickly. Combining ammonium with phosphate application can be good too. So giving the plant a little bit of a boost in terms of vegetative growth and stimulate root growth, so that they'll then be able to access the phosphate as well, can work. And also the acidification effect of ammonium can sort of inhibit some of the short-term fixation of phosphate by soil minerals. Adjusting soil pH, that's obvious. Yeah, we know that supply of phosphorus, availability of phosphorus is particularly governed by soil pH. We know we're aiming for that 6.5 range. So adjusting or liming, just like we did in the lab the other day, to bring that soil's pH up to 6.5 is important. Recycling organic matter, big source of phosphorus. If we can recycle more of that in agricultural systems, we can improve efficiency and availability of phosphorus. And then there's buckwheat in that picture. I don't know if you recognize that crop. And that's a green manure crop that has been found to be quite efficient at taking up phosphorus compared to other crops. So if you compare a soil with the similar phosphorus levels and you grow buckwheat compared to some other crops, the buckwheat will tend to take up a lot more phosphorus. It's quite effective at that. And I know there's more and more interest in growing it as a green manure in this country, and also for biodiversity purposes. The flowers are great for bees, etc. So it's one to look at in flower-rich margins, or as a cover crop. Potassium, not so many strategies to recommend. It's been suggested that more frequent annual applications of potassium can reduce risk of leaching, fixation, and imbalances. So the luxury consumption, so a little bit more often is recommended, rather than just putting a lot on every 5 years, which then might sort of flood the system and lead to leaching, and also be taken up in excess of what the plant needs. So testing the soil regularly to make sure that you know how much potassium you really need to apply. And then crop residues are really high in potassium, especially straw. So returning straw to fields or manure, if possible, is another way to really improve the efficiency of potassium use on your farm. And yeah, the next one, this isn't actually tomorrow, but the next one I'll talk about is nitrogen fertilizer theory, and then we do have a practical coming up later this week as well. Practical is actually on Friday, not Thursday. Sorry, that's an old slide from last year. But yeah, we'll do a practical, and there's an assignment based on this as well that is assessed right on nutrient management planning. So you'll need to know how to use the tables that I showed you and how to do some of those calculations.